Good afternoon, everyone. Welcome to our dynamic talks at Grid Dynamics. We are very glad that you have joined us. I see that we have new connections every minute, so I think we will wait for maybe 1-2 minutes and we'll start. And now I want that Marika will say something about our company.
Yes, of course. Hello, everyone. And until we're waiting, we will talk a little bit more about Grid Dynamics. The Grid Dynamics is a leading provider of technology consulting, engineering, and data science services, Fortune 500 corporation from financial, technological, and retail sector. Our company has been operating since 2006 and is headquartered in California and has development centers in United States, Eastern and Central Europe. So as of today, Grid Dynamics brings together more than 3,500 engineers in 14 different countries. As you can see, we have a large amount of different offices in different countries, and we continue to grow up steadily. So Grid Dynamics is a NASDAQ-listed public technological service company with core expertise in big data, data science, machine learning and AI, scalable omnichannel services, DevOps, and cloud enablement. So also you can find more information on our site, griddynamics.com. And to understand who we are working with, you can see the list of our partner and clients in different spheres like tech, finance, retail, and others. So more information you can find also on our career side. And if you want, until we're waiting for people to join, you can go by this QR code to our site and search for some career opportunities if you want, or read more about our company. So thank you for joining.
And now I will talk about our instructions for today meeting. During the lectures, you can ask questions via Zoom chat. After the report, the speaker will answer them. Please note that the questions will be seen by all participants of the meetup, or you can use your microphone to ask questions. So I will invite our speaker, Iñigo San Aniceto, our staff big data engineer at Grid Dynamics, who will cover the topic Spark Performance Mastery. So Iñigo, I think you can start.
Okay, so welcome everybody to today's webinar on Spark optimizations. In today's webinar, I will first do a recap the basics of Spark to let everyone on board and make it easy to understand when I talk about some of the optimizations. But before I do, I would like to talk briefly about myself. My name is Iñigo San Aniceto. I'm a staff big data engineer at Grid Dynamics with over 5 years of experience with Spark. And over the last 5 years, I've worked in several companies listed here at positions that involve heavy usage of Spark. So in today's agenda, as I briefly mentioned earlier, I will do a quick recap of Spark to get everyone to the same level. Then I will introduce the sample data that is going to be used throughout the examples. Yeah, so I've created an example for each of the performance optimizations that is going to be presented. This sample data is public and you can download it, so you can do the same test that I am going to show here. And once I do this quick recap and explain the sample data that is going to be used, I will go into the 4 optimizations that we are going to discuss today. Those are going to be first cache and persist, that is used to speed up algorithms in Spark. Then we will talk about data partitioning and data skewness. We will see how it impacts performance and how we can fight it. Once we finish with the data skewness, we will move into optimizing Spark joins to avoid performance bottlenecks. And finally, we will talk about mapPartitions and how they can be used to improve performance. Yeah, so these are by no means all the optimizations you can do in Spark. There are many others, but these are some of the most important ones. Yeah, caching your data correctly, partitioning your data correctly, doing optimized joins in Spark will assure you that your code is performance in Spark. Okay, so let's start with a recap of Spark. Before anything, we should talk about what is Spark. Spark is a big data processing framework, that can be accessed in 4, 5 different languages, depending on how you see it. So it would be Scala, Python, Java, R, and SQL as well. And the most important thing to notice about it is that when you program something on Spark, you are not actually working with a single computer. You are going to be running with a cluster. That means you will have a driver and you will have several workers. And the first thing you need to do when you start writing a program is learn about your environment. Yeah, you need to know how many workers you have, how much memory they have, and so on and so forth, because this is going to be very important when we start optimizing. In order to do that, you have 2 options. The first one is to look at the Environments tab in the Spark user interface that I will show in a minute. And a different one is to just go into the Spark session and get all the configurations to see what you have there. So let me switch my screen. This is my IntelliJ project where I've created my examples. At the moment, I am running this example that has launched a Spark session. And whenever you launch a Spark session, it will automatically create Spark UI where you can see what's going on. And this is what I have here on my Firefox window on the right. So here you can see the environment. Yeah, so you can see some information about your environment, like the Java version, the Scala version, the Spark properties that we have. And you can look at the executors as well. Yeah. So in this particular case, because I've created the examples with my computer, I don't have access to a cluster. Yeah. So you will see that I only have one driver. This driver has 8 cores. Yeah. So there will be some parallelization, but it's not a full-blown cluster as you could have on a real productive system. But still, as you will see later on, it's enough for the optimizations that we are going to show. Okay, so we've seen what's a Spark, and we've seen how to check the environment, and the executors that you have. Okay, let's move on. Start with partitions. So when you write code in other programming languages, such as Python or Java, usually when you read a file, to process it, you will read it as a whole. However, we've said that in a Spark, we are not working with a single computer, we are working with a cluster. So in a common scenario, you are not going to work with a single file, you are going to work with a directory. And when you read, you are going to read the entire folder. These files are not going to be processed all at once, but instead they are going to be divided into what we call partitions. And the number of these partitions will depend on many things, such as the configuration of your cluster. But by default, Spark will set up chunks of 128 megabytes. So if the input files are bigger than 128 megabytes, it will automatically split those files into blocks of 128 megabytes, and it will process them separately. So what will happen is that one of these partitions will go into one of these worker nodes, and the other partitions will go to additional worker nodes, obtaining some parallelization. Okay, let's move on to the next important thing to understand when we work with a Spark. In a Spark, we have lazy execution. What does that mean? Let's see it by comparing it to other programming languages that you might be aware of, Java, Scala, or Python. In Python, for example, if I say x equal 2 and then y equal x times 2, the variable y is just a pointer to memory where the value 4, in this case, is stored. In a Spark, if we think of a similar example, we wouldn't have the value 4, but we would have the instructions to arrive to that value. So we'll have the instructions listed, and only if we request the value to be either displayed or recorded or somehow if we retrieve that value, then the recipe is going to be computed. And this is going to be of extreme importance, as we will see later on. Okay, so we've seen that the Spark is lazy, and we've seen that it has partitions. Now, this recipe that we talk about, how is it going to be created? Well, Spark has what we call transformations and actions. Transformations are those that build this recipe. Yeah, as I mentioned, it could be things like filtering, selecting. Yes, if I have a table, I could select some columns, filter some rows. Those would be transformations. And then I have actions. Yeah, actions are what will trigger execution. So for example, if I want to write the result into a database, or I want to display it in a screen, yeah, at that moment, Spark needs to perform an action, because otherwise it cannot give me a result. And within the recipe, within the transformations, there are two types of transformations. They are those that we call narrow transformations, where, as you can see by the arrows, one step of the recipe can be computed just looking at the previous partition, or at most a couple of partitions that are known. And then we have wide transformations, where in order to compute one step of the recipe, we might need to look at several partitions of the previous step. Yeah, this is easily seen with a filter. Imagine you have taxi rides for historical data, and you want to filter those that happen on a particular date. If I do a filter, every executor, yeah, so every computer within my cluster can independently compute the result. Yeah, because it doesn't need to know about what are the records in other partitions to give me an answer. However, if I do a join, yes, so if I take one table and compare it with another table, then each partition needs to know about what's going on other partitions, because otherwise it wouldn't be able to compute an answer. Yeah, as you can probably imagine, wide transformations are the ones that will most of the time give us issues in Spark, because in narrow transformations there is no bottleneck. Yeah, in wide transformations we will have a lot of network traffic between the nodes in the cluster, and this, if not done correctly, can slow down the execution. Okay, let's move back a bit just here and remember what I said about lazy execution. Yeah, I said that this recipe is built and not executed immediately, but we wait until there is an action in order to optimize. Yeah? And I've mentioned that these are the types of transformations we can have in the middle. Now, how does Spark optimize these transformations? It does so by something that we call the catalyst optimizer. So because we have a recipe and we don't actually execute the recipe until we need to cook it, yeah, so until we need to write it into a database, or we need to display it, Spark can actually decide how to do it most efficiently. Yeah, so it will take the parse logical plan. This is the input that we have introduced, and it will optimize it looking at the data to give me an optimized physical plan. Yeah? This physical plan can actually be seen using explain. So if you take the name of a data frame and you do explain extended true, you will see these four parts. So you will see the parse logical plan, the analyzed logical plan, the optimized one, and the physical plan. Yeah. Once again, I will talk about this in the first example, actually, and you will be able to see it better. Yeah. So this is just as a recap of what's happening under the hood, but the example will make it clearer. Okay. So that's all about the recap on Spark. Now what we are going to do is we are going to explain the sample data that is going to be used in the webinar. So in order to create the examples of the performance optimizations, I looked online, and this is the data that I found to be the best fit. Yeah, I took the New York Taxi and Limousine Commission webpage, and in here you can find a lot of data. Actually, ranges from 2009 to 2012 about 4 types of different taxis. So there is yellow taxi, green taxi for higher vehicle, and high volume for high vehicles. And this data is going to be, it's stored in Parquet. So it's already columnar and compressed, which is good for Spark. The sample data that I downloaded, it's not all this historical data that I told you about. I've only downloaded the data that is available for 2021 and 2022, and only the ones for yellow taxis. It's in total around 700 megabytes of Parquet files. So if you know a bit about big data, you know this is not big data. Just 700 megabytes is nothing. But it's, again, big enough to show the performance optimizations that I will do. Just to give you an idea, the data contains around 44 million records. Okay, so with this, I'm going into the first performance optimization. But before that, maybe we can do a quick round of questions. So if anyone has something that is not clear that we need to discuss before moving on, please speak now. Otherwise, I will assume that everybody understands the basics and I will follow on. So I'll give 30 seconds. Yes, you can also, I'm looking at the chat. So if you can, otherwise I'll assume that it's fine and I'll continue. We can always answer questions at the end as well. So I don't see any questions. So I assume that we are good to go. So I will start with caching in Spark. So caching in Spark is one of the most important things to improve the performance, and it's directly related with what we've talked about the recipe. Yeah, the variables, the data frames within our Spark program won't hold the data in memory. They will hold a recipe to how to get them. Yeah, and we've seen that the reason for this is that the catalyst optimizer will optimize what we introduced, the parsed logical plan, into a physical plan that is optimized. Now we are going to see how this affects a particular example. So let's start with some code. Here, in the first line, I'm going to read some data from a folder. Yeah, so Spark, read Parquet, and the folder. This is going to read the data that I've told you about in the sample data, yeah, the taxi rides. So it returns me a data frame called taxi rides. Now, in order to see what is Spark doing, I'm going to run .explain on taxi rides. And this is what I get. Yeah, this is just a screenshot of the things that I'm interested in. So it's a parsed logical plan where I can see a relation. So here what I am seeing is the columns of this data. Okay. Now what I do is I will do a couple of operations. So I see that there is a column called pickup date time, which is a timestamp, and I'm going to convert it to a date. So I say to date to get high date, and I'm going to filter it between the 1st of January and the 31st of January. Now, if I do explain again, look what happens. These taxi rides, it's not reference. What we are doing is we are increasing the recipe. Yeah, and you can see that the recipe needs to be written from the bottom up. So we have a relation, yeah, the same one that we had here. Then this with column is the projection. Yeah, so in the projection, further down the line, there will be a write date as to the date of this particular column. And finally, we have the filter. Okay, so nothing weird until now. Yeah, only what I've already explained. We are building a recipe, and Spark is storing the recipe in a logical plan. But what happens if I carry on and I say taxi rides of January 2022, and I want to filter those where the trip distance is bigger than 10? Yeah, if I go here to the middle, I just see that this was the parsed logical plan that I had, and now I add the filter. Okay, but what is happening in the optimized logical plan? Well, first of all, look at the one on the top. the one on the top still has every operation, but in the optimized logical plan, the filter has changed position. So Spark thinks it's better to first read the data, then perform the filter, and finally do the project. And observe that in the filter, it has actually changed the order. And now look what happens if instead of doing this directly, I do a cache on the previous operation. Yeah. So remember, the previous operation was taxi rides January 2022. And here I do .cache. When I do .cache, the parsed logical plan still looks the same, but the optimized logical plan is not looking at the source of the data anymore. It's looking to an in-memory relation. Yeah. So to make an analogy, when you do a cache, you actually store in memory the previous data frame, and you are converting it in something similar to a variable that you know from other computing programming languages. Yeah, it's not exactly the same, but it's something similar. Okay, so what we are going to do now is we are going to see how to use this to improve the performance. And I'm going to execute this example for that. So in this example, yeah, what I'm doing is I'm taking the source data, which is the New York taxi data that I've told you about. It's all here. Yeah. I'm going to, well, first read it, then filter it. Well, in the example, it says 1st of January to 31st of January, but here I'm actually doing it for several months. And then I'm going to group it, perform several filters. And the difference here is that if I decide to cache, I'm going to store this in memory, and otherwise I will just recompute every time. Okay? To show the difference, I've introduced here explain, which is the first operation after the cache. So I'm going to run it once. It asks me whether I want to cache it or not. I will say no, just to show you the difference. And while this executes, I want you to look here on the right. So this is the Spark UI that we discussed earlier when we were looking at environments and executors. It can also be used, and it's mainly used for debugging the performance of your Spark code. So here we can see the jobs. If we drill down, we can also see the stages, and we can see the partitions as well. Yeah, so if I go into one particular stage, I can see what's going on. I can see the different partitions, and here I can see how much it took my Spark session to execute each of these partitions. Okay, we will use this in more detail later on when we analyze joins. Okay, so without using cache, what I see is that my execution time is around 12.5 seconds. And you can see that the first took 5 seconds to compute, the first operation, which is the computation of the rate statistics per day, and the rest around 2 seconds. Now, let's repeat this, but this time I'm going to cache the operation. Yeah, so remember that this, what it does in here, it caches the result of this group by. Just one note here, doing .cache or doing the temporary view and cache table, it's the same. Yeah. The difference is that here in storage, which is what I'm going to show you now, I get a nice name if I do it this way, and otherwise I will get a very weird name. Okay. So notice the difference with earlier. Yeah. Before we had, I think, something like 12 seconds. And now I just have 6.6 seconds. So it's way faster. You can see that the first operation, there is no much difference, but in the additional operations, we've lowered from around 2 seconds, 1.8, to around 0.2 seconds. So by caching, we have avoided doing repetitive processing the same thing several times, and that has speeded up. Yeah, and you can see it by looking in the physical plan, that as I say, we are printing, because here we are doing an in-memory table scan. So we are looking at something that is already cached. What I wanted to show you here in the Spark UI is actually how caching is taking a space in memory. So if I drill down, I can see the 8 partitions of my taxi stats per day, which is the group by that I was executing here. And I can see where it is stored. As you can see, this is very tiny data, because actually when I group by day, I just get over 400 records. So it's in the kilobyte order. But this gives you an idea of how you would look, whether the memory that you want to cache can fit in your cluster or not, in your cluster's memory or not. Okay, so we've seen these UI windows on the example. We've also seen the storage, and we've seen something similar to this. Yeah, so here on the left we have the example that I've just shown. Yeah, so doing some aggregation and then using a cache to compute some further statistics. And on the right, I have another example that I'm not going to show, otherwise it would be too long, but the idea is similar. Yeah, once I do the first operation, the additional operations become much quicker because of this cache. So which are the general rules for caching? Well, the first one is that caching has a cost. Yeah, caching the data frame forces materialization. Yeah, so once you write it or you display it, it needs to be stored in memory. So the first query, in some cases, it can be slower. Yeah, depending on how much data you cache. But as we've seen, it will pay off in following queries. So in general, don't cache what is easy to recompute or is not reused several times. And cache only the necessary rows and columns. So filter and select first before doing the caching. So we've been talking about cache and persist, but so far I've only created an example with cache. What is persist? So persist is the same as cache, but it allows you to set up different storage levels. So cache is memory only, while persist can be memory only, but also memory and disk, or even disk on its own. Sometimes when you think about the Spark, you think about in-memory processing, because that's what everybody always keeps repeating. So you might think why you might want to persist something in disk. Well, that could be the case where you are working with a data that is very large, so it doesn't fit in memory, but it's still very expensive to recompute. Yeah, so if it is large and it's very expensive to recompute, it might be worth persisting it in disk. And finally, which ones are the algorithms that will benefit the most about caching? Well, those are obviously going to be iterative algorithms. So algorithms that look and access the same data over and over again. For example, those in ML are the ones where caching is going to have an enormous impact, because you are going to save the data once, and then every time that is reused, it's just looking at the memory and not being recomputed. Okay, so I've seen that there are some questions. What will happen if you cache too big table and the table is too big for memory? So what will happen is that some partitions might be dropped. And if the partition is dropped, so here you can see, if the partition is dropped, what you get is that it will need to be recomputed. Yeah, so Spark will still work, but it will be slower. Yeah. The other one, it will throw out of memory error. Well, actually, you will get a warning, but it wouldn't stop the execution. Okay. So let's move into fixing data skew. So at the very beginning, I've explained how Spark doesn't process all the data at once, but how it divides it into chunks and processes those chunks in different executors. But what happens if those chunks of data are not evenly distributed? Yeah, that's what we know as data skewness. Yeah, so usually this appears when there is a filter or there is a join. So we are going to first see how we can identify it, and then how we can fix it. So to identify data skewness, we have two main options. So the first one is to look at the task in the Spark UI. Yes, so I've shown you earlier where you can look for the task. And in the task, Spark gives us a statistic of how much time it took to execute the tasks and some other information like the memory and so on. So if you see that the median task or the maximum task took much longer than the median task to execute, that means that you have data skew. And I will show later on an example where this is very clear. Another option to look at data skew is to get the number of records per partition. Yeah, so you can do a map partition, get the size and collect it. And then with this, you can compute the statistics such as median, max, standard deviation, and so on. And that will also allow you to find data skewness. So what I'm going to do now is I'm going to move into another example. So this time I'm going to show you this example. First, let me show what we are doing. What I'm doing here is I'm reading New York taxi data. Once again, I've created a function that's called print partitions. Yeah, so basically it will show me how much records I have per partition. We will see that it has a skew, and then we are going to repartition it to see how it is fixed. So let me execute it. And while I'll execute, I'm going to display the Spark UI. Notice as well that here in the Spark UI, I've introduced text hints. So you can do that using a Spark context step job group. So this allows you to introduce here, you see here this read, show, print partitions, and the description. That then makes it much easier to find where in your code you are. Yeah, because sometimes a single line here could generate several jobs or several tasks. So it's easier to look at it if you give yourself some hints. Okay, so we are starting to see the result. So this is the data that went in. It has 43 million records, as I told you earlier. And as you can see, it's more or less evenly distributed. Yeah, the number of partitions, the number of records per partition is around 3 to 5 million records per partition. But notice what happens when I first filter. When I filter, this data is not evenly distributed across the partitions. So you can see that some partitions have a lot of records, but there are a lot of partitions that don't have any record, and there are some that are in the middle. In order to solve that, you can do actually two things. One of them is coalesce. So coalesce is an arrow transformation. So it tends to be quick, but it has one problem, and it's that you are not going to be able to increase the number of partitions. So for example, in this example, my input had 11 partitions, yeah, and the output, in order to do it efficiently and create something that is evenly distributed, I need to say 3, yeah, because if I try to do it in 4, it will put all together these small partitions, but it wouldn't be nearly as big as the big ones. Having only 3 partitions, it's a problem here, because my cluster, as I've shown you earlier, has 8 cores. So if I do any further processing with just 3 partitions, I'm going to have some evil partition. However, if I do repartition, repartition is going to be a wide transformation, so it's going to be slower at first, but then I will benefit from this prioritization of my cluster in upcoming operations. Yeah, and I can see that if I look at stages. Yeah, so here I can see what happens when I have 24 partitions. You can see that when I write this to this, which is something very easy I can do, the median is 1 second, the maximum is 2 seconds. Yeah, and now compare that with what happens when I don't still have that repartitioning. So let me find it out. This is the coalesce. So it should be here. Yeah, so here you can see that I only have 3 partitions. It can take longer to execute. yeah, because I have some cores in my computer that are idle. Okay. So we've seen how we can create data skewness with a filter. We've seen how to repartition to fix it. And well, this is an example that I got from a previous run, yeah, where it was very clear that before repartitioning, one of the partitions was much bigger than the others. And as you can see, from this point to this point, only this partition is being executed and the rest is being idled. Yeah, while when repartitioning, everything is distributed better. So the cluster is not idle, and the result is better. And this is just the summary of the statistics I got from the previous example. So what are the general rules? When filtering and when joining, we can create an uneven size in the partitions. So when we are filtering, we can do a coalesce after the filter, yeah, or sometimes repartition. Yeah, usually you would do a coalesce if you have big data because it's going to be enough. But sometimes, as we have seen, it could be beneficial to do repartition to even out even more. One important tip here is that if you are using a Spark 3, you will have something new called iterative query execution. That basically what it does is, let me go back. Here, it introduces a feedback loop with the statistics about the data. And with that, it's able to optimize the partition. This adaptive query execution, it's enabled by default in a Spark 3. But if you're using a Spark 2 for 8, which some of you might be using in production, you can enable it. Yeah, so just be aware of that because that will allow you to remove some of the hassle of repartitioning yourself. The other thing is joining. So when you join, it can also happen that one of the column by which you are joining is not evenly distributed. And this can cause a strong data skewness. So imagine that we want to compute some stats at city level. And for that, you are joining two tables. Big cities will likely have much more records than small ones, creating skewness. Okay? So the solution in this case is broadcast if possible. Yeah, because if you broadcast the smallest table, you will fix some of these issues because it will be a map side join. You can also use adaptive query execution, which can be set up for skew joins. So just set up in the config spark.sql adaptive skew join enabled true. And finally, you can also apply something called a salting technique that we will see in the joining section. Okay, so let's move into joining with a Spark. And before going into optimizations, I would talk about the different types of joins that we have in Spark. Yeah, and then I will show an example. So when I talk about different types of joins in Spark, I'm not referring to the join types as we refer to them in SQL, like inner join, left outer join, right outer join. Those are the types of join determined by logic. Yeah. But what I mean by types of join is how Spark is going to perform the joins internally. So there are three main types. Yeah, there are more actually, but these are the three main types. There's the shuffle merge join, the shuffle hash join, and the broadcast join. The fastest one is broadcast join. Yeah, so the broadcast join, which is here on the bottom, what it does is if there is one table that is small enough to fit in memory and small enough to broadcast it around the network, it will broadcast it to every executor. And by having that small data frame in all the executors are able to perform the join, a partial join on the map side, and then in the reduce side, just collect the data. And that makes it very, very fast. Yeah. Then let's talk about the slowest one, so the other side. That's the shuffle merge join. So in here, we need to shuffle the data. We need to sort by the key on both sides. And then we need to iterate on both sides to get the join key and reduce it. Yeah, so this is the slowest one, but it's the default one in Spark. And the reason it's the default one is because it works most of the times. Yeah, it's rare than a shuffle merge join fails. And then we have the one in the middle, which is the shuffle hash join. You can force shuffle hash join by basically saying that the preferred sort merge join is false, which is the default setting would be true. Yeah. And in here, we have something in the middle between a shuffle merge join and broadcast join. So basically, there is a shuffle phase, the same, but then in the source phase, the smallest side is hashed and bucketed. Yeah. Then the smallest side is joined with the bigger side in all partitions. So with this, we can make it much faster. So what I will do now is I will move again to an example. So this time, example is this one. And in this one, what we are going to do is we are going to take, once again, the same New York taxis data, but I'm going to get additional data. I'm also going to get taxi zones because in this taxi rides information, the zone, so basically the neighborhood, is obtained with an ID. And this taxi zone is a dictionary that gives me the name of that ID. And then collisions. So there is also public data on New York collisions. So you can see how many vehicles has crashed in one particular hour, one particular day in a particular neighborhood. And the idea of this join, the idea behind is to get an analysis of whether the crashes impact the taxi ride times somehow. Yeah. So what I do is I group the collisions by crash date, hour, collision borough, so the neighborhood, and then I will do one optimization. So I will first show the example without and then with the optimization, which is repartitioning the input data. And finally, I will do another optimization, which is broadcast. So the first example will be without any optimization, then with just repartition, and finally with broadcast as well. So let me run this code. Let me refresh this. So I will say I don't want any repartition and I don't want any broadcast hint. Okay, so in the meantime, I'm going to show you the result here because that way it will allow me to do it a bit quicker. So when I don't do any optimization, the result is going to be around 129 seconds. Yeah, it can change depending on how busy my computer is, but it's going to be something like that. When I repartition, it's going to be about 50 seconds. And when I broadcast, around 16 seconds. So you see that with these optimizations, and this is on my local computer with some small data, I've managed a 10x, nearly 10x, 9x performance increase. And if you look at the logical plan, you will see that the first two will do a sort merge join, while the last one, where I hint broadcast, it's going to do a broadcast hash. Okay, so let's move to this and see what's the status. It's running. It's still taking some time, so I will show you the slides that I have created. So in the first slide, we can see one case where there is a very, very strong data skewness to the point of nearly breaking everything. And this was done on purpose by colleagues in the group. And you can see that the lapse time was 248 seconds. And notice the maximum execution time of the partition. Yeah, it's 2.4 seconds when there is a lot at zero. And notice as well, there is a shuffle spill to disk and to memory. Yeah, if you see these numbers, especially if you see them this high, there is that's a very high indication that something is terribly wrong. Okay, let's see if this is finished. Still not finished. So let's see what's going to happen when I do repartition. Yeah, so when I do repartition, we will see that the skewness is not going to be this big. There is still a skewness. As you can see, there are some very big partitions, but because it has already been repartitioned, there is, yeah, every partition is doing something. And the final time of the join is reduced to just 50 seconds. And the last one is going to be a broadcast. So when we do broadcast, it's going to be a map site join. So we will have as many partitions as the map site. And you can see that this is much more balanced and also much faster. So let's see if this has finished. Yeah, so it has finished 135 seconds. And if we look at distribution, this is the distribution. Yeah. Let's re-execute it, but this time, well, I will just skip the repartitioning, and I will show you with both optimizations, yeah, to save some time, because I think we are a bit struggling with time. So this should take about 20 seconds. So it should be fairly quick. This is with all the optimizations. So what I've done is, again, I repartition on the columns that I am going to use for the join. So Spark knows where to find those values, and that's why it's quick. And in the broadcast, I say to Spark, please broadcast the smallest data frame. Yeah, so that's why it is very quick. So this should finish in a couple of seconds. Let's just wait, and then we move on. Should be ready soon. Okay, so it's finished. It took 18 seconds, so you can see that it was much faster than earlier. Yeah, and if you look at the partitions, you will find what I've just shown here, something very, very similar. So let's find the general rules about the Spark joining. So the first one is filter select the data frames before the join to try to reduce their size. Ensure that the inputs are correctly partitioned. And the same thing that I've said earlier applies here as well. If you are using a Spark 3, or if you are using a Spark 2.4.8, where you can activate adaptive query execution, do it, because that will help you. For broadcast joins, you can hint Spark in two different ways to do a broadcast join. The first one is by using broadcast. This is a Spark SQL function. And the other one is by increasing the auto broadcast join threshold. By default, it's 10 megabytes. If you increase it, data frames of bigger sizes are also going to be increased. If one of the data frame is not small enough to broadcast, but it's not too big either, you can consider also disabling the precursor merge join, because this can also improve the performance. Yeah, and if everything is failing, shuffle merge join is usually the safest option. If this is not working, check out your partitions, because there is some data skewness that you have in there. Okay, and this leads me to the last section, which is map partitions. So this is going to be actually the simplest example of the ones that we are going to do, probably after the one of cache, which is focusing on an arrow transformation, like a map, that takes one partition and generates one partition, and map partition that does the same, but in a different way. So how it is different? Well, you can see it here with picture. In map, when we take one partition, we will do a call per element. So every element will call the function in map, while in map partition, there will be a single call. Yeah, we can see this in this slide. Map is a transformation that is applied to every element of the RDB. So there is one call per element, and map partition is applied on every partition of the RDBs. There is one call per partition. There's one thing to notice here, which is that map and map partitions can be applied to RDBs and datasets, but not to data frames. So the first thing that you need to do if you are using a data frame is to convert it into a dataset. Here you have an example of how to do that. So here I have my data frame. Once again, my New York taxis data. I select the columns that I'm going to use. So pickup location, delivery location, pickup time, and drop-off time. And here I use a case class to convert this into a data set. So a data frame is just a data set with type row. Yeah, if you convert it into a case class, you type it and you convert it into a data set. Okay. So which are the benefits of mapPartitions? Well, because they only call the function once per partition, they can avoid repetitive heavy initialization. And they are aware of the partition, so you can do partition-wise processing. An example of repetitive heavy initialization that could be useful is, for example, if you have some personally identifiable information, you could use it to say in which computer, in which worker has a particular record being processed. So let me show the last example. So let me open example number 4 and run it. And while it runs, I'm going to show you what's going to happen. So in this example, I call with the same data 2 different functions. The first one is map, yeah, that just takes the pickup location, delivery location, write time, and host IP. And the second one does the same, but because we are processing with mapPartitions, it will only get the host IP once, and it will use it for all the elements inside the map. Yeah, because remember that one partition is going to be processed in one executor. Okay, so if we see how this goes, well, in here I'm also doing the comparison not just between map and mapPartition, but also with column with UDF. It should finish soon, and it should give us the result that we are looking for. Okay, so here you can see to get the same information. Yeah, so same information with column plus UDF took us 29 seconds, with a map 28 seconds, and with mapPartitions 4.8. Yeah, there is no caching here, so this is just how much time it took with the different methods, and you can see that by using mapPartitions, I got a 6x speed up over map for this example. And this is the last optimization. So to summarize, in this webinar, we've seen first a quick recap of the Spark architecture. And then we've seen 4 optimizations that are quite common. Caching and persisting, and we've seen why this is important and why it makes sense in Spark. Data skewness, yeah, so this is very related with how you partition your data. We've seen how to optimize Spark join to avoid bottlenecks. And if you remember, we've obtained something like 9-10x speed up. And finally, we've seen how to use mapPartitions to improve performance. So from my side, that's all. Thank you very much. And now if you have any question, I will be happy to answer.
And we have one question in chat. I don't, yeah, 2 minutes ago. So I think that we don't answer it. Or
what is the, well, I see that there is a question. What is the cost of converting a data frame to a data set? So let me go back here. A data frame, as I say, it's a data set where the object it's a row. While in a data set, you have a case class, so your columns are typed. This has advantages and disadvantages. Disadvantages, a data set can be slightly slower than a data frame. Advantages, data sets are typed, so you will get typing errors before you execute the code. And it will also give you access to the RDD API. So you know how in data frames we have a high-level API where we can do things like select, filter, group by, join. But there is another list of lower-level APIs like map, group by, reduce by, and stuff like that that you can use with datasets. Yeah, so with datasets you can get kind of the best of both worlds. But usually you would only do it if you need this RDB API for something. Otherwise, you would stick for data frames. Okay. Will these slides be available to us by any chance?
Yeah, I answered that we will share the recording of this meeting on our YouTube channel so they can see the presentation too. Do we have any other questions? You can unmute.
Yes, actually, I have one more question. So what will happen in case we apply coalesce and got partitions, amount of partitions less than we have cores? What will happen in that case?
What will happen is that those cores will remain idle. Yeah, so imagine if you have eight cores and you do a coalesce 3, you will have 5 cores that will remain idle. Yeah. So it's actually something that has been shown in one of the exercises. I don't know if I've shown it here. Maybe I've shown it on the exercise, but there was an example, the one with coalesce and repartition actually, where we were doing coalesce 3 and we were seeing that some of the cores of the executor were idle. But you need to think that when you filter heavily or when you aggregate heavily, the data that you will have is small, can be small in some situations. And when it's small, parallelization also has a cost. Yeah, so creating very small partitions, partition with a few records doesn't make sense either, because the scheduling cost and so on will also damage your performance. Yeah, so you need to find a balance between the number of partitions and the records inside this partition.
Okay, got it. Thanks. Yeah, thank you.
Any other question?
I think that we don't have any questions more. So thank you, Iñigo. Thank you for this presentation, and thank you everyone who joined us. It was a great talk, I think. And we would like to send you this recording on your email that you left us. So have a nice evening, and we'll see you on the next our big data talk.
Thank you. Have a good day.